Simple.
Yeah, like this. Yeah. Yeah. Mm-hmm. We'll continue anyways. We'll go to the next lesson now. Okay. Alright, so if you want to write this down, this is our next lesson. Simple harmonic motion. Do you want to send a message to Gail telling her we're starting now? Where is she?
Okay.
Yeah.
Where is it go?
Very big
Yeah.
and planet,
Hmm?
planet, moon, earth.
Huh?
Means
Yes.
planet. Where is
Planet?
planet?
Moon? Yeah.
Yeah, she is on her way.
Okay. Well, let's start then. Alright. Simple harmonic motion. If you can write this down somewhere.
Okay.
You got this, Khalifa? Simple harmonic motion. So, let's continue. Hmm? 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 So, see, it's a big lesson. Lots to do. Lots to do. Okay, so firstly, this motion, yes?
Yes.
What's wrong?
It's too many.
Yeah, so that's why we start today and finish on Monday.
Yeah.
I said, don't worry. So this motion, we see this motion in physics. It's a special type of motion. It's called simple harmonic motion. It's motion like this, up, down, up, down, up, down, or left, right, left, right, left, right. This is simple harmonic motion. What's wrong? What's wrong? It's okay?
Yeah.
Okay. So it's like just like with circular motion, there's a special force that causes this motion. So do you remember for circular motion, to make something move in a circle, you need to have a force that moves towards the center and is perpendicular to the velocity. Now we have something that's like this. It's going left and right, and left and right, left and right, for example. So here it is here. What makes it move like this? Yeah. Now let's see what type of force. If an object is undergoing simple harmonic motion, then there's a force that is proportional to the displacement. Let me explain what that means. So there's a force here, and this force is proportional to x. So if you make the distance twice as big, then this force becomes twice as big. Have you seen this symbol before? No. No, you haven't. So what it means is if the x multiplied by 2, then the f is 2 times bigger as well. Yeah? Okay. So there's a force here which is proportional to the x and acts in the direction opposite to the displacement. So what I mean is this force moves left when this tries to move right. It'll move left. So look, here. As this moves to the right, there's a force. And the force gets bigger. So if this is twice as big as this, then the force is twice as big. And if it's 3 times bigger, then it's 3 times bigger force. And if this is moving to the right, then it means the force will be to the left. And if this moves to the left, force to the right. Okay? Oh, you missed this? Oh. Proportional. So it means if the x is twice as big, then the f is twice as big. If the x is half, then the f becomes half. Yeah? You look confused.
Yeah, I know now.
Oh.
Maybe.
Okay.
Yeah.
Okay. So write this definition down carefully.
What's the topic? Just
Simple harmonic motion.
all of them?
Just the box. Yeah?
Spring.
Hmm?
Springs.
A spring is a simple harmonic motion. This is a spring. This. Are you asking me what a spring is?
Oh yeah.
Yeah, this is a spring. So you can imagine it goes like this. Go. This is called simple harmonic motion. Is it okay? Yeah. Or like this. Yeah? It's okay?
Yeah.
Are you sure?
Yeah. Just
Huh?
a tire.
It doesn't have to be a spring. No, it could be, there's many things. Okay, continue? Right. So, imagine you pull the spring out and then release it. What does the velocity time graph look like? So, here's the spring. Okay, and you pull it out to here and you let go. And let me draw it the other way actually. Here it is here. And you pull it out to here and you let go, and what happens? It goes right, left, right, left. Right, let's think about what the velocity time graph would look like. So, at the beginning, will it be big, small? What do we think?
Big.
Yeah, well, at the very beginning. Yeah, just at the very beginning first.
Big.
No, it'd be 0. Because if you pull it out and hold it and then let go, it starts at rest and accelerates. Yeah?
And suddenly high speed.
Yeah, and then suddenly high speed. So it will increase. It will be going fastest when it's here. Then what happens when it passes the middle, like when it's here? What happens to its speed?
Suddenly.
No, it'll slow down. It will start to slow down and then it will stop. It stops when it gets to the end here. Then what happens? It speeds up, but this time it's going left. So its velocity is negative. So you get the same thing again. So the graph looks like this. Yeah, it's kind of the same shape.
But it's no more than the original place.
Hmm?
Never more than far than the original place.
Yeah, it's let me draw it a bit smaller. It goes like this: up, down, up, down, up, down, up, down. Yeah, and it never goes past the original. Yeah, this is what it looks like. Yeah. That's if you pull it to the left. If you pull it to the right, it'll be the same except just upside down. If you, yeah. So that's what's happening here. Okay, so some terms now for and some of the terms are the same as circular motion. So, for example, F. F is the same meaning. So the frequency is how many cycles in a second. T is also the same meaning. The time to go from the start to the end. The same meaning. And the omega is the same. But this is a little bit strange because there's no circle. So here in the circle and in the simple harmonic, where it moves here to here, the F is the same meaning. So for example, if F is 2 Hertz, then it means in 1 second it goes around twice.
Right.
And the T is 0.5, which means it takes half a second to go around once. Same meaning here. Here, 2 Hertz means in 1 second it goes twice. And time, half a second, means it takes half a second to go 1 cycle. But the question then is, what does the omega mean here? Here the omega means this angle. But where's the angle for this? So there isn't an angle because it's moving in a straight line. So it's kind of confusing. How could the omega be the same? So, what does the omega mean? I give you a picture to try and help. Okay, this is a good picture to explain.
How are they going like this?
Huh?
This is going like this.
Yeah, well, what type of motion is this? This is a circular motion. Yeah? So this has an omega. Okay? Now, this piece here, it's going left, right, inside of this. Left, right, left, right, left, right. The omega for this is the same as the omega for this.
That goes left, right, but this actually goes like
This goes around in a circle,
Yes.
and this goes left, right.
Yes.
This is simple harmonic motion, and this is circular motion. If the t is 1 second here, then the t is 1 second here. If the f is 1 Hertz, then here the f is 1 Hertz. If the omega is 1 radian per second here, then we say this has 1 radian per second, even though we don't see the angle. Yeah, I'll give you another example, okay? This is the example my teacher gave me. So if you imagine, okay, it's an old example. Record player. Do you know these?
Yeah.
You do? Okay. They spin around. They play music and they spin around, okay? And here you have a wall. And imagine here you put a candle. The candle has a little flame on it. Like this, okay? And this makes a shadow on the wall here. Now, what way will this shadow move? Will it go up and down?
Right.
It'll go right and left. Okay? So it'll move across here.
And
When it gets to here, it's here.
yeah.
And then when it starts to move, it'll move back. Now, this motion here is simple harmonic motion. And the omega is the same omega as for here. So there's actually a relationship between simple harmonic motion and circular motion. There's a relationship. Circular motion is 2-dimension, 2D. Simple harmonic motion is 1D. But there's a link between the two. They're directly linked. Simple harmonic motion is circular motion, but in 1 dimension. Can you see that? It's quite interesting. You would not think that this is circular, but it is circular. It's just circular in 1 dimension. This is circular in 2 dimension. What do you think? Yeah, it's okay. You get the idea? Yeah. So You don't need to draw this. It's okay. So Ft and omega are the same. Oh, and if you want to see a picture of this, you can go to this website. It's okay. Right. So there's some new words. So any idea what equilibrium or origin means? Yeah.
This was the learning.
You learned equilibrium with me a few weeks ago.
Both sides are equal.
Yeah, so in the simple harmonic motion, where's the equilibrium? It's here in the middle. This is called the equilibrium, okay? It's the center of the motion, okay? The next one is the amplitude. What's the amplitude, do you think? That's okay, because it's a new word. The amplitude is this distance here to here. That's the amplitude. It's the maximum distance from the displacement. It's the limit. Yeah? Velocity, you know velocity. Angular frequency, the omega, you know this. Frequency, you know this. Time, you know this. So these two are new. You need to write these down. I think you should write all the words down. I think it'll be good for your English, help you remember them, right?
Okay.
Good answer somewhere. Ready to continue? Great. Now, let's have a look at the energy now. So when the mass is at its maximum displacement, it's at rest. Therefore, it has no kinetic energy. It has only potential. And it starts to move. Its potential energy gets converted into kinetic energy. When it's at the origin, it has no potential energy and has only kinetic energy. This is when it's traveling the fastest. So what would the energy graph look like? I'm actually going to draw it here, and you can draw it too. So what we'll do, here I'll put x in meters, and there's 0, and here is minus a, and here is a. And on the y-axis, I'm going to put the energy, and that's going to be in joules. Okay. When the particle is at the very end, what's its kinetic energy? So here it's moving left and right, left and right, left and right. When it's at the end, what's its kinetic energy? What do you think? Yeah, because when it's at the end, it stopped, and then it comes back. Then it stops, and it comes back. So at the end, it's 0. Now, when it starts to move back to the center, what happens to the kinetic energy?
Back to center?
Yeah.
Bigger.
It's getting bigger. So it'll go up, 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 like this. But then when it passes the center, what happens?
Slow down.
Slow down. So the kinetic energy goes back to here. So this is KE. Now remember, we said you can't create or destroy energy, only convert it. So when the kinetic energy is low, the potential energy must be high. And when the kinetic energy is high, the potential energy must be low. So when there's no kinetic energy, you must have a lot of potential energy. And as the kinetic increases, the potential must decrease. So it goes down to here. It's the opposite. And then it goes back up to here. Finally, wait, potential energy. If you add the potential energy plus the kinetic energy, you'll get the total energy. But the total energy doesn't change. It's constant. So you have a line here, and this line is the total energy. It doesn't change. So like here, this is the total energy. Half of it's kinetic, half it's potential. This is the total. Most of it is kinetic, and here a little bit is potential. You add these two together, you get the total. It doesn't change. It's a constant. Okay? They ask you to draw this graph in the exam, so you need to copy this neatly. I need to move this a bit.
What's TE, total energy?
Total energy, yeah. And this is energy in joules. Yeah.
P is
Potential
So
energy.
you add the potential energy and the kinetic energy to give you total energy.
Yeah. Yeah. You drew this?
Yeah. Oh, sorry. Draw wrong.
You did draw it wrong.
Yeah.
but maybe not.
Mhm.
I don't think you will have potential.
Yeah, you do, but it's a different potential. It's not MGH. It's a potential energy inside the spring.
MGS.
Not MGS either. A different formula for this problem. Yeah. It's not MG anything. There's no G in it.
Oh yeah.
Yeah.
So not it doesn't MGH why we call
There's
it-
no MGH because it's moving like this. So there's no height. It's on the ground.
or why we call it
Yeah, I understand. Same word, different meaning.
oh
Which?
It's a different. It's not like the potential energy last time. It's not MGH.
FS?
It's not this either. We have to do the formula. It's a new formula.
Oh,
It's
it's
a new
not,
formula.
oh, it's not working then.
Yeah, no, it is, but it's a different formula. It's a different one. We're doing it today. Don't worry.
Oh.
Okay. Yeah. Just it's not MGH. That's all you need to know. It's not MGH. It's a different formula. Because the H is 0.
yeah.
Yeah. Remember. Go. Listen. Remember, I said, listen carefully. I said potential energy is because of its position. Because if it's up here, you can knock it and it will do work. Yeah? Understand?
Yeah.
If you have a spring and you pull it to here, it has potential energy because if you let go, it will do work. It'll do work because the spring pulls it back. It will do work because the earth pulls it down. It's the same idea but different formula. Yeah.
Can we calculate
We can calculate it.
this?
We'll do it later.
Okay.
Yeah. Right. So we drew this anyways. Okay. Now we don't need to write this, but it's just the same as earlier. Earlier we did this graph, remember?
Yeah.
Velocity goes up, down, up, down, up, down, up, down. Okay. Now, remember the acceleration is the slope. Yeah? So here, the acceleration, is it positive or negative? It's going down, it's negative. And here, positive, negative, positive, negative. So you can see that in this graph, it goes negative, positive, negative, positive. Yeah. And the same thing here with displacement. It goes left, right, so it goes up, down, up, down. So all of these graphs are the same shape. All the same shape. Right, now on to some formulas. So the first formula, the same. T equals 1 over F, the same. Okay. Next formula, also the same. Also the same. This is a new one. The acceleration is minus omega squared s, where s, sorry to be clear, if you start here, and this is minus a, and this is a, and here it is moving, the s is its displacement s. So the reason that the a is minus is because, remember I said, if it's on the right, then the force is to the left. So that's why it's a minus. Yeah? So this is a new formula, minus omega squared s.
So A is acceleration.
Yeah.
Acceleration related with force.
Oh yeah, of course. But go. Of course acceleration is related to force.
Sorry.
You know this. Good thing I'm giving you a test next week. I can see what you know. Alright, continue. You got these so far? Yeah? Yeah? Okay. So, next. The next is the formula for S. Now, there's two situations. Situation one. It could start here and then move right, left, right. Okay? And then you have situation two is where it starts here at the end, at rest. And then it'll move left and right. Okay? So here we say it starts on the inside, and here we say it starts on the outside. If you want to calculate the S for this one, it's A sine omega t. And if you want to calculate the S here, it's A cos omega t. So for example, if you want to know here when t is 1, where is it? You want to calculate the S. Then it's A sine omega 1. Okay? So you have two formulas. It's A sine if you start from the equilibrium. Otherwise, it's cos if you start out here. So you have two formulas, okay?
So A is S.
The A
The A, the big A, the capital A is displacement.
is amplitude, is maximum displacement.
Is not from center to here? Is maximum?
It's from center to the end.
Okay. How about if go back? So this.
A doesn't change. It's constant. So look here, look. Here's the center. Here's minus A. Here's plus A. So this moving, this is S. So S is 0, 10, 20, 30, 40, 50, 60, 70, and then it's equal to A. And then it gets smaller, S gets smaller.
Okay.
So the S moves between minus A and plus A.
Always A.
Yeah. So like you can think about it like this, go. The S is between the A.
Okay.
Yeah.
So the S does not have a particular value.
Yeah, S is a variable, it changes. A is amplitude constant. Continue?
Otherwise,
Yeah.
it means
Oh, if it's not the center, then you should use cos. Otherwise.
A cos.
Yeah, A cos omega t, yeah. Yeah? It's okay? Continue? Next formula? The next one's for the V. So, you use A omega, cos omega t, if it starts from the equilibrium. Otherwise, use minus sign. So that would be minus A omega sine omega t, if it starts at the end, instead of the middle.
Middle is inside.
Mm-hmm. Yeah?
Yeah.
Continue? Yeah? Okay. The last one is the V, or not the last one, is the V. Now, the reason for the plus or minus is because if it's here, the V is negative, and if it's here, the V is positive because it heads to the right, and here it heads to the left. So the plus and minus is because it could be going left or right. You need to decide. Yeah? Continue?
The T is the same.
Hmm?
T is the same.
T?
2T. So we.
Oh yeah, same answer. So the difference is, Ben, if you know the time, you can use this formula. If you don't know the time, but you know the S, you can use this formula. You get the same answer. Yeah? Now, the potential energy. So, the potential energy, let me think, let me show you. If you look at this graph, what shape is this?
U.
Yeah. So in maths class, what's the name of the shape, these problems you did in maths class? You know them, begins with a Q. Quadratics.
I write it.
Yeah. So this maybe shouldn't surprise you. The formula for potential energy is a half m omega squared s squared. S squared. So if you go back here, this is, oh sorry, I called this x, but it's also called s. You can use x or s. So s or x, whatever, sorry. You can see that this shape here is an x squared shape from maths class. So this formula shouldn't surprise you that there's an s squared in it. So when the s is big, the potential energy is big. And when the s is 0, potential energy?
Zero.
Yeah, 0, yeah. So when the s is 0, you've no potential energy. And of course, the kinetic energy is the normal formula, a half mv squared for kinetic energy. Yeah? Now, just actually to think about this. Kinetic energy is a half mv squared. Potential energy, we have it here, a half m omega squared s squared. Yeah? The kinetic energy plus the potential energy is the total energy, which doesn't change. Okay? So a half mv squared plus a half m omega squared s squared, that's equal to the total energy. And that never changes. So, if the v is big, then the s must be small. And when the v is small, the s must be big. Because the total has to stay the same. Yeah? Okay. Right, do you have all these formulas?
Yeah.
Yeah? Okay. Now, in the... What are we doing for time? Yeah. In the real world, this doesn't really happen. Will this continue like this forever? No, what will happen? It'll eventually stop. So it'll go like this. And then stop.
Yeah.
Okay. This is called damping. In the real world, the graph looks like this for the x. Sorry, I keep saying x and s is the same thing. The graph looks like this. It goes up, down, and then it slowly comes to rest. Okay. This is called damping. Now, we won't study this. You just need to know the word for the exam. But the formulas are more difficult if you have it like this. Because it's more difficult. I won't say any more. So what I want you to do is maybe just to copy this with this word in your notebook. Damping, yeah. It's not a dumpling, actually, yes.
Yeah, I'm just hungry.
You're hungry, did you not have lunch?
Not too much.
You didn't, you're in GNIB. Did you have lunch?
Wasn't
Not much.
it?
What did you have?
Donuts.
Donuts for lunch.
And coffee.
That's terrible. Such a bad lunch. Why did you have this for lunch?
Just didn't prepare. It's like too fat in the restaurant. In the school restaurant.
What did you have for lunch, Ben?
Chicken filling and cheese.
Nice. No? Summer? I know what you had for lunch. You had 2 cigarettes and a cup of coffee.
Actually,
3 cigarettes?
he is
Cook
better.
Better?
myself.
Very bad. He cook by himself.
Oh, did you?
Yeah.
Something nice?
I think it's good than the schools.
Better than the school?
Yeah.
Very nice.
Very nice? What did you cook?
Vegetable and with some beef.
Okay. That's better than donuts and coffee, isn't it? And better than you. Yeah.
I think I need
He should cook
coffee.
for you guys. Shouldn't you?
It's too many.
Okay. Maybe someday. Right. Now, this one here. Let me try and explain. So first, imagine this is not moving. And this one here is moving. So you see small x. Goes left, right, left, right, left, right. Okay. Then you come along and you grab this and you start to push at it. Okay? So, of course, if you move the big X, it will affect the small x. Right? So if you start pushing at it here, then it will affect here. My question is, how can I change the amplitude here? I want to make this move out more. You know what I mean? Like I want it to go out further. So what could I do? There's some things I could do. I could maybe move this very fast. So I could really push it fast. Maybe I should move it slow. Like, what would be the thing I should do to make this move out really far?
Move harder.
Yeah, so you think maybe move faster? Yeah?
Harder.
Or harder? So what do you mean by harder? Yeah, okay, so that means you make the A here really big. So you move this out very far. Yeah. Now what's interesting is the F, the omega, and the T does not change. So imagine here that this has a frequency of 2 Hertz. So it means in 1 second it goes back and forth twice. Okay? You cannot change that by forcing it. You can't change that. So if this has a T of 1 second, it goes right, left, back to the start. You can't change that, even if you force it. Only the A changes. And now the next question is, how does the A change? So you might think if the A here is big, then the A here is big. But that's not actually it. You get this interesting graph. I'll try and explain it here. I'll draw it. So here is the frequency of your hand, and here is the amplitude of the small one. Okay? So you might think if you push this really fast, so that means the F is really big, then this will move more amplitude. So you might think the graph might look like this. Yeah, getting cold. But it doesn't. It's quite surprising. The graph actually looks like this. If you move it too fast, you actually get less amplitude. There's some point here where you get the most amplitude. And what that point is the frequency here. So what I mean is, imagine that this is moving at 2 hertz. 2 hertz. If you want to make this move out further, what you need to do is also move at 2 hertz. If you move at 3 hertz, no good. If you move at 1 hertz, no good. But if you move at 2 hertz, the same as this, you will get more amplitude. So this is kind of interesting result. So can you picture, this is moving. If I move with 2 hertz as well, what will happen is this will move out more. Okay? This, I didn't write the word down, but we call this resonate. If you can match the frequency, we say we resonate. Now wait, before you draw this, let me give you an example. You know when you see the person who sings and they break the glass? You know this, okay? How does this work? What happens is the atoms, they're vibrating here. So they're the little atoms, they're moving back and forth. They're moving back and forth, okay? So they each have a frequency. It's a very big frequency because it's moving very fast. If she can sing at the same frequency, then you make the amplitude bigger. And if the amplitude gets so big, then the glass shakes and breaks. So this is called resonate. You make the glass resonate. You match the frequency. Yeah? So what you need for the exam is this graph, because they sometimes ask you to draw this graph for the this situation. So you need this graph here. Yeah. How are we doing here? Okay. We got perfect timing. Okay. So what we'll do is we'll finish on this, and then the next class we'll do the examples. You got this?
What's the name called? Reads and
Oh, sorry, yeah, resonate. Resonate means basically you match the frequency. Got it? Close it? Yep. Right, try to get all those questions from this week finished for Monday, because we'll have a tutorial on Monday.